In this tutorial, we're just going to go over how to determine the rate law if you are given initial rates. So as mentioned before, with the rate law, you can't just figure this out by looking at a chemical equation or by looking at the coefficients within that equation and using those as subscripts, or superscripts actually. You do need to go about an experiment to be able to figure out your rate law. Now, the type of experiment that you would use is just basically you'd have a reaction and you would begin to change the concentrations of the reactants within that reaction. As you change those concentrations, you'd measure your rate of the chemical reaction using those concentrations. Now, when you do that, you then go and calculate your exponents by using these concentrations. And you'd also be able to figure out your rate constant as well, once you figure out your exponents within your rate law. So let's just go through a simple one first, and then we'll get into one that's a little bit more difficult to do. In this case, when you have this type of problem, you'll notice that you have a chart, usually, where it'll have a list of all your reactants, and in that list you'll also have different concentrations, the concentrations that you're changing, and then the rate that you measure once those concentrations change. Now what we're going to do is actually do a ratio of rate laws between the two different trials that you have here. So for example, let's first put the rate law of the second trial in this case. So if we were to go and do that, we'd end up with rate, and just to distinguish the trials from each other, we'll do it as rate 2 equals, you usually have a rate constant, which is K, and then the concentration of your N2. And we'll label this with a 2 because of the fact that we're dealing with the second trial. Now what we're going to do is put this over the rate law of the first trial, so it would just be rate 1 equals, well, the equal sign's already there, so we don't need to put it again. And then we'll have that over the K, which the K's in this case can cancel out, they're going to be the same thing. And this will be over the concentration of NO2 originally, or during that first trial. So now you have something like this, and this is all to a power that you don't know. So we're just going to label that power as M. So now what we need to do is figure out what that M is going to be. We already have our concentrations, we already have our rates. So now we just have to figure out this exponent. So let's just plug in our numbers. So rate 2 in this case would be 28 times 10 to the negative 5 over our first rate, which is 7.1 times 10 to the negative 5, equal, again, the rate constants were the same, so we don't have to worry about those. Now we're going to put the concentration of the second trial, so it would be 0.020 over the first trial, which is 0.010, and that's all to the M power. What we want to do is divide those out. So if we divide those out, we end up with 4 equal to 2M. And from here, you could probably go and figure out M, which M is just going to be 2. Now, for those that don't work out nicely like this, what you do is take the log of both sides and then figure out M from there, which we can go through within the next problem. So in this case, we just figured out M. Now we want to figure out what our rate constant is going to be. So all we need to do is plug in the numbers from one of the trials into our rate law. So our rate law is just basically rate equals the rate constant times the concentration at a particular power. So the rate in the first trial, 7.1 times 10 to the negative 5, equals the rate constant, which we don't know, times the concentration, which in the first trial was 0.010, and that is all to the M power, which we figured out M to be 2. So now all you're doing is solving for K, which is your rate constant, and if you do that, you end up with a K of 0.71. So that's the way to figure out your rate law from initial rates. Again, do that ratio of rates, between, let's say, your final trial and your initial trial. Once you figure out your exponent from there, then you can go and plug everything back into one of the rate laws to be able to figure out your rate constant. So now that we've gone over one that was rather easy, now let's go over one that's a little bit more difficult. In this case, if you notice, you have 3 different reactants, and then you have 4 different trials for those reactants. So if we were to do out this rate law, we would have the rate equal the rate constant times H2O2 to the m times I minus to the n, and then times H plus to the p. So as you notice, there are going to be 3 different exponents in this case that we need to figure out. Probably the easiest way to do this, though, is to try to get our ratios to have all the values be able to cross off except for one of them. And I'll show you what I mean in a second. So let's just say we want to focus in on the H2O2 for now. So if that's the case, if we were to go up and look at our chart, what we want to do is make it so that the I minus and the H plus cross off because of the fact that they have the same values. So if we do that, we can go and look at trial 1 and trial 2. You notice that for the H2O2 you have 0.010 and you have 0.020. They're 2 different numbers, but as far as the I minus goes, those are the same, and then as far as the H plus goes, those are the same. So those are going to cross out if we were to go and do the ratio of the 2 rate laws. So knowing that, what we can do is actually do rate 2 over rate 1, just like we did in the previous problem, equal to the concentration of the H2O2 for the second trial, which was 0.020, and that's going to be over the H2O2 concentration for the first trial, which was 0.010, and that's all going to be to the m power. So now what we can do is set that equal to the rates now. So the rate of the second trial was 2.3 times 10 to the negative 6, and that's going to be over the rate of the first trial, which is 1.15 times 10 to the negative 6. So now we just have to go and do out this math, and if we were to do that, we end up with 2m equals 2, and so m in this case is just going to be equal to 1. So we went and we were able to figure out our first exponent. Now let's try to figure out the exponent for the I minus, which again, what we want to do is try to get 2 trials where everything else is the same except for the I minus concentrations. So for example, if we were to look at this one, we could look at trial 1 and then trial 3. Because of the fact that if we compare the H2O2, these values are the same. If we compare the H plus, those values are the same. So that takes care of that. As far as the I minus goes, you'll see that it does change. So that's what we're looking for. So as always, make sure you put the later trial up top and then the initial trial on the bottom. So rate 3 will go on the top. So you have 2.3 times 10 to the negative 6 over 1.15 times 10 to the negative 6, and that's going to be equal to 0.020 over 0.010, and we're looking for the n exponent in this case. And if we were to go and do this out, we'd end up with 2n equals 2, so n equals 1. So we were just able to figure out another exponent. Now for the last case, we want to make sure that the H plus is the only thing that changes. So the ones that we can look at in this case are, let's say the first trial and take the 4th trial. Because in this case, H2O2, H2O2, they stay the same. I minus here, I minus there stay the same, and it's only going to be the H plus that changes. So let's go and put this in. So you have 1.15 times 10 to the negative 6 over 1.15 times 10 to the negative 6, and that's going to be equal to 0.001 over 0.0005, like that. And we're looking for p in this case. Now for this, we end up with 1 equal to 2p, which p is just going to be equal to 0. because anything to the 0th power comes out to be 1. So now that we have all our exponents taken care of, now we can actually go and write out our rate law. So we end up with rate equals k, H2O2, which we found out to be to the 1 power, so we can just leave it as it is, I minus, again to the 1 power, so we can leave it, and then the H plus was to the 0 power, so we're just not going to put it in at all. So the rate law in this case would just be rate equals k times H2O2 times I minus. So now if we wanted to figure out the k, let's just take the first trial here and plug everything in. So you have 1.15 times 10 to the negative 6 equals k 0.010 and then 0.010. And if we were to solve for k from this, we'd end up with a k of 0.0115. So that's how you go and figure out a rate law using the initial rates. Again, if you're given a table that looks like this, where you have a series of trials with different concentrations for each of your reactants and also the rates, what you need to do is try to narrow it down so that you're taking 2 trials where you're able to cross off most things except for one of the reactants, and then keep going until you're able to figure out all the exponents from there.